Radioactive waste final disposal is global. The nuclear scientists are not the only ones concerned about it. It concerns everybody. Nowadays, world researchers agree that it is necessary to make storage facilities deep underground to isolate the level long-lived radioactive waste for the entire period of their potential hazard. However, construction of storage facilities for centuries is impossible without a long and painstaking research work. Therefore, creation of underground laboratories is a well-timed move to ensure environmental safety in the years ahead. Moreover, the underground research centers are successfully established around the world. Hokkaido Island is the northmost point of Japan. There is a large port city, Wakkanai, here. Just 50 kilometers away in Horonobe Prefecture, the underground research laboratory is located. We conduct experiments studying the properties of geological environment and possibility of deep earth radioactive waste placement. We have several stages of research program. The first is the surface research, and the second is studying the rocks after the underground workings are laid, including research with use of radioactive waste simulators. Research work in the underground laboratory Horonobe started in 2001. Scientists carry out all tests at the depth of 250 meters. This is what the special mines look like, cut down in the sedimentary rock, where simulators of radioactive substance are laid. The main target of the researchers is to understand whether the rock is able to restrain the spread of radionuclides, and if so, for how long. To do this, the rock is heated, filled with water, and changes of its properties are observed. This is the place where we test the engineering safety barrier system. Now we're collecting chemical parameters of water around the safety barrier system. This is the place where we test the engineering safety barrier system. Now we're collecting chemical parameters of the water around the safety barrier system. We have identified several main areas for the research: verification of the barrier system, possible packaging corrosion, and geological formation properties. We do not use radioactive elements, but the simulators only in our research. Horonobe is an international project. Together with Japanese scientists, their French and Swiss colleagues conduct research here. There is a common practice for nuclear industry, as safe radioactive waste disposal is a global problem. The estimated time of the project is about 20 years, so we're ahead of following plan. We have planned to publish the results of the work this year. And after that, we backfill the underground mine. We have agreed so with the local authorities. Indeed, the Horonobe object was created not for the waste storage. Its purpose is research work. Besides the underground Horonobe laboratory, research is performed at present in the Mutsunami Center, but it studies mainly the granite rocks. Together with the researchers, the search and feasibility study of the eventual site for radioactive waste final disposal is done here, in the State Organization for Radioactive Waste Management (NUMO). The task of the specialist is to calculate all risks, including possibility volcanic eruptions, tsunamis and earthquakes. There are many natural disasters in Japan, such as volcanic eruptions or earthquakes. These effects are taken into account at first instance when creating a laboratory. Security barriers are no less important issue. One of the basic matters is natural barrier. Therefore, we conduct a thorough analysis of the placement site and the rocks. A complex system of engineering barriers is planned in the final disposal place, in addition to natural barriers. All waste will be glazed and placed in special cans. Their wall thickness will come to 20 centimeters. This is necessary to prevent radioactive substances entering the groundwater, and thick layer of clay impervious to water will protect the storage from external effects. The setup process for the final radioactive waste disposal complex takes about 100 years. Look, exploration goes on for about 20 years. Analysis of the terrain is performed. Further, about 10 years come for the underground laboratory construction, and it may take about 50 years to fill the final disposal point with radioactive waste. But the decision on where to build the facility will not be taken without taking into account the views of the local residents, communication with whom is based on full trust. At the same time, there is almost no fear of such objects. Moreover, the management of the Japanese municipalities itself submits applications for the future repository to be located on their territory. After all, its construction brings plenty of benefits for the locals, including workplaces. NORW organization holds special meetings with local residents in every region of Japan since 2014, performing active awareness-raising activities. It is necessary for the population throughout Japan to know about the problem of existence and placement of radioactive waste on their territory from the competent source. We are always open to dialogue. Japan is one of the countries that decided to preserve nuclear energy, while some of European countries plan to get energy not from the peaceful atom, but from the renewable sources such as windmills and solar panels. However, as the experts say, even complete refusal from the nuclear industry will not solve the problem of the existing radioactive waste final disposal from nature and the human living environment. The Alps are the highest and the longest European mountain range, stretching across the 8 countries. The International Research Laboratory Grimsel is located here in Switzerland in the Ahr mountain range. The scientific site is located in the mountain tunnel, a little more than a kilometer long. Initially, the tunnel was intended for the hydroelectric power station, but in 1984 it was given to nuclear scientists for the research. At the first stage of experiments, we are looking for appropriate ways to evaluate low permeable rocks. In the next set of experiments, we used water with radioactive particles and observed their behavior inside the rock. The third stage was an engineering experiment for testing our developments in order to study their long-run behavior. In 2012, Swiss scientists, together with colleagues from Japan, South Korea and Sweden, constructed a full-size model of the final isolation complex in tunnel for the radioactive waste generated not only in the nuclear industry, but also in the medical and scientific sectors, as well as in the security sector. Grimsel Laboratory is currently testing 3 types of barriers that together should prevent the spread of radioactive substances. They are containers, betonite clays and massive rocks. There is an 8-meter layer of betonite clay behind this concrete wall, which we use for testing, namely for gas transfer through the engineering barrier. Its study is of importance as storage of low-level radioactive waste generates gas, and we don't want that gas to stay in our storage. In the experiment, we can use only types of gases, with behavior similar to that of the gases generated by a radioactive waste. There are, for example, hydrogases of methane. And as the scientists joke, the experiment is not highly scientific. However, it demonstrates clearly the behavior of betonite being one of the key materials of engineering barriers in contact with water, which is the main enemy of the underground storage facilities. Here you can see the betonite behavior pattern. As soon as it comes into contact with water, it absorbs it and swells, increasing the volume. The increased volume allows sealing the area around the waste containers. This is the first important property, and the second is that due to swelling, betonite can fill small gaps in the geosystem. It is a great luck for us to get the experiment site. After all, this is a closed zone of control over radioactive radiation. Look, scientists have placed radioactive tags in the cavities carved into the rock. And now they track the movement of the isotopes in the rock. If you look in this compartment used to monitor and control the experiment, you can see the hoses that carry the radioactive tags into the rock. These experiments are designed to assess the radioactive tags behavior. Here you see a typical composition which includes tritium being a poorly sorbed element and, for the example, cesium as well sorbed one. The goal is to have a mixture of various radionuclides that behave differently in the rock. Swiss scientists have completed the necessary set of studies and were ready to finalize the work here. However, partners from the other countries asked for continuation of research activities, as Grimsel is primarily a major international scientific project. Every year, the researchers working with the Swiss laboratory Grimsel, as well as specialists of NAGRA, the national operator for final radioactive waste isolation, visit more than 20 exhibitions in areas where it's possible to construct the facility. The target of scientists is to tell the locals about their work in detail and clearly. To do this, they also created a virtual tour of the future point of final radioactive waste isolation. A few years ago, the Swiss voted against our project of deep final radioactive waste isolation. But we think that society will accept our ideas within 15 years. And then we will organize another national program before the next voting in Switzerland. We will travel around the country educating people. Since Switzerland is small, not like Russia, it is only 4,000 square kilometers. It will not be a great piece of work for us. Swiss researchers have decided that counting on the type of geological rocks is not practical. That is why they opened a scientific and experimental site in the canton of Jura as well. Scientists have built an underground laboratory in the northwest of Switzerland. There is a research site at the depth of about 300 meters inside the Monterey mountain, in the thickness of opaline clays, where experts are studying the possibility of radioactive waste final placement. Opaline clays is unique. It has a high level of water resistance, which allows for reliable isolation of hazardous substances. Upon the completion of research works, it is planned to build a deep-seated place of RW final isolation. It will be located 100 kilometers from the laboratory among the picturesque Alps. Opaline clay is a special geological rock because it was formed about 180 million years ago in the Jurassic period. And it is of interest for scientists as clay is an excellent isolating material, poorly permeable to water, which prevents spreading of radionuclides efficiently. This rock has several advantages. First, clay can retain radionuclides. Its sorption capacity is very high. Secondly, clay stops water. As you can see, it's dry everywhere. Water doesn't enter the tunnels and accordingly will not wash radionuclides out from the packages. Thirdly, clay starts to expand when exposed to moisture. Accordingly, in case of earthquake, it makes a crack. It closes gradually. And radionuclides do not manage to spread towards the surface. However, these are not all the unique properties of the opaline clays. The fact is that during the deep disposal of the containers with the radioactive waste, hydrogen is produced and accumulated due to the radiolysis and corrosion. In turn, it raises the gas pressure, and this is dangerous for the integrity of the storage. But we can avoid the damage. After all, scientists from the Monterey found the microbiocenosis in the clays of the Middle Jurassic that consume hydrogen and reduce the gas pressure under the ground. We were greatly surprised finding out existing microbiological activity here, that is, the sulfate bacteria consumes hydrogen. This is one part of experiment that aims to show what happens when a steel canister is corroded underground. There are several units here. Right now only one of them is working. This one with a canister inside. We can inject hydrogen into it, into a system with bentonite and clay, and use radionuclides to observe various chemical reactions occurring at the microbiological level. We do not use waste, we use radioisotopes labels like sodium-21, strontium chloride, but in very small concentrations. As the Grimsel de Monterey laboratory is set up solely for research purposes, only after the scientists are convinced of the safety of isolation in the particular rock, the place for the final isolation of radioactive waste will be selected. Underground research laboratories exist in all countries that produce nuclear energy on large scale. For example, in France, research has been conducted for more than 20 years to understand whether it's possible to dispose RW in clays. In Germany, a wide range of host blocks is under construction nowadays. Sweden and Finland have relieved on massive rock. The Belgian nuclear industry choose boom clay for safe disposal of the nuclear industry waste. The underground Hades research laboratory, located municipality of Mont d'Isère, has been operating for almost 40 years, and this is the first center of this kind of world history. In the world history. Of this kind in the world history. Initially, the laboratory consisted of one shaft and two galleries. However, scientists realized fast that they need a second access shaft for testing integrity, which is created to the depth of 220 meters. Now we're on the border between the new part, built in the 2000s, and the old part, created by the pioneers in the 80s. There is a sample of clay we've been studying for 40 years. This clay is from the depth of 200-300 meters. It has a number of unique properties for isolation of intense waste. Clay is rubber-like and elastic, which is important from the point of view of mechanics. It also contains water, but it is stationary, placed in closed cavities. It's perfect natural barrier. Boom clay contains minerals that can absorb radioactive particles, preventing their spread. Look, these sensors track chemical, mechanical and hydrological characteristics of the clay. After the scientists placed their radioactive tracers in it. We use radioisotope atom tracers and radioactive substances in the experiments primarily to understand the mechanism of radiation spread. For example, we have installed pipes with filters and we put there small amount of radioactive material, thereby contaminating water. We do this 051620 to study the time needed for the radioactive substances with water to fall into the soil. According to the Belgian nuclear scientists, boom clays are an ideal natural barrier for the safe storage of high-level radioactive waste. Although the experiments have not yet been completed and the place for construction of the final RW isolation point is not defined, experts from the Belgian Nuclear Research Center have already achieved consensus with local people. There is an information center of the territory of the research laboratory, which is annually visited by more than 3,000 people. Here the scientists explain the RW future in Belgium in hundreds of thousands of years. Finding out the conditions the society would accept us, we faced certain requirements. It concerned employment for the local population, health issues, and now, 20 years later, we almost have a license to store radioactive waste. And we also want to be sure that we comply with all requirements that the local population put forward to us in the very beginning. This is confirmed by the fact that local residents continue to interact with us and take part in our work. Today, foreign experience of nuclear scientists is important for Russia more than ever. After all, our country has already accumulated more than 500 million cubic meters of RW. And this figure is a bit but growing every day. But don't be scared by this. The fact is that devices using radiation surround us everywhere, in airports, in the subway, and even in hospitals. For example, gloves and grooves from radiological departments are also radioactive waste. And in order to isolate them for the entire period of potential hazard, we need safe storage facilities. And as you know, any scientific victory comes after years of painstaking research. Nizhnekamsky rock massive, unique gneiss rocks, located here are about 2.5 billion years, and they are stronger than granite. According to the nuclear scientists, there is an ideal natural barrier to protect against the spread of radionuclides. This is why a unique underground research laboratory for Russia will be built here soon at the depth of about 500 meters. Here, scientists will find out whether it's safe to store high and medium-level long-lived radioactive waste. Scientists have been choosing the site for creation of laboratories since the early 90s, for almost 20 years. Initially, the territory near the closed nuclear city of the Zheleznogorsk was chosen according to the number of geological, economic, social and other aspects, where the mining and chemical plant was already located, and the legendary nuclear enterprise, which history has been developing since 1950s. Further, 20 promising sites were identified within 100 kilometers. Then, the scientists selected 5 sites, of which 2 remained later for the most detailed study. Comprehensive studies of the surface and in deep wells have shown that the Yenisei section of the Nizhnekamsky rock massif is most suitable for the construction of the underground laboratory. The underground research laboratory in the Nizhnekamsky rock massif, in 6 kilometers from the Zheleznogorsk, Krasnoyarsk Krai, and 4.5 kilometers from the Yenisei River on the territory located in the vicinity of the mining and chemical combine. The structure of the Nizhnekamsky rock massif laboratory, which will be located at the depths of 450-525 meters, includes 3 vertical shafts, technological, auxiliary and ventilation, as well as horizontal working passing along the counter. Studies of the massive rock will begin from the start of laboratory construction. Sampling of the rock samples, cores, will be performed at different depths. Thermometrical control and thermophysical experiments will be carried out, as well as the study of the chemical composition of rocks and groundwater, tracer experiments to determine velocities of the groundwater movement, the study of filtration and migration properties of the massive. In general, the laboratory will conduct research in 150 years. Specialists have developed a strategic master plan to be extended in the course of scientific research. Since the start of construction, scientists will study the structure and hydrological characteristics of the rock massif. After construction of the Nizhnekamsky rock massif laboratory, in situ experiments will take place in the underground workings created specifically for research between the auxiliary and technological shafts. The laboratory will carry out the final stages of the development of technological operations for the radioactive waste management and design studies, as well as insulating properties for engineering barriers previously studied in ground conditions. Specialists will work out technologies for creating vertical production wells for final isolation of Class 1 radioactive waste, as well as conduct seismic and geodynamic studies. Geomonitoring will be done during the underground laboratory operation. A demonstration and research center will be located on the surface of the Nizhnekamsky rock massif laboratory to test non-standard equipment for the transport and technological operations of radioactive waste management on simulation spatial models, mock-ups and samples, training of production personnel. Ground facilities of the underground laboratory are under construction on the territory of Nizhnekamsky rock massif. Parallel to mining operations, scientists start experimenting designed to study the insulting properties of natural barrier under conditions of radioactive waste disposal. Along with this, engineering barriers will be tested. At the same time, research is carried out without use of radioactive materials, and the placement of RW can become possible only after confirmation of the object's safety and carrying out public hearings. Research work will start from the beginning of tunneling. When we go underground, shafts will be created and research carried out in parallel. The mountain bridge will be studied. A lot of experiments are expected. All objects are unique and they have their own characteristics. There are no identical ones. And we have our own feature both in regard of design and the depth of occurrence and rocks. The key enemy in the long-term disposal of radioactive waste is water, which can transfer radionuclides into the water-bearing formations and thus into the zone of human activity. According to experts geologists, there is a little water in natural cracks of gneiss rock in the Nizhnekamsky Massif. Moreover, according to the results of preliminary studies, these waters will not come to the surface even after hundreds of thousands of years. Isolation is also facilitated by the fact that radioactive elements are inherently unstable and decay at their own rate. The half-life is the period of time during which the nucleus loses half of its radiation activity. For any radioactive substance, the initial radioactivity is halved after one of half-life, decreases 4 times after 2 periods, 8 times after 3, and more than 1,000 times after 10 half-lives. The half-life is different for various isotopes. Thus, for example, the half-life of radon-222, which exists in nature, is only 3.8 days. Iodine-131, 8 days. Cesium-131, 9.7 days. Cesium-137, 30.1 years. Plutonium-239, 24,110 years. Uranium-238, which exists in nature as well, 4.5 billion years. For geological final isolation of RW is necessary to talk about half-lives from hundreds and hundreds of thousands of years. No matter what skeptics say, the issues of safe radioactive waste storage in our country are under focused attention. An international crystal club was created which united Russia, Czech, Romanian, German, Swiss, Japanese and South Korean nuclear scientists. One of the club meetings was held in Krasnoyarsk. Thus, foreign colleagues were able not only to exchange experience, but also to assess the tremendous work carried out by Russian researchers. Our mission is safe isolation of radioactive waste. This problem goes in hand with the issue of obtaining cheap and efficient nuclear energy. Hence, our goal is to isolate RW for centuries safely and not to shift this problem on future generations. The underground laboratory should be built by 2026, and from then a new stage of research will begin, until experts finally make sure that the radioactive waste is placed here safely. Whatever it was, we give ourselves a chance for secured environmental future, creating the Nizhnekamsky Rock Massive Laboratory in Zheleznogorsk.